Hi class, welcome to our second lecture of chapter 5 for quantum mechanics. Again, our main reference is Introduction to Quantum Mechanics by David J. Griffiths, and I recommend that you buy this book. You can buy it online, as this will help you in understanding the lectures. So we accidentally stopped at the atoms, but in this lecture we will continue with the atoms. So for a neutral atom with atomic number Z, it consists of a nucleus, which is very heavy, and you have a charge also revolving around the nucleus, and they are the electrons. And if there are Z protons in the nucleus, you will also have Z electrons that's revolving around that nucleus, because the atom is supposed to be neutral. So you have electrons which are not massless, so they have mass m and charge negative e, as opposed to the positive charge of the protons. So the Hamiltonian for this system would be composed of three terms. This is the kinetic term, and the potential, Coulomb potential between the nucleus and the electron, and you have also the interactions of electrons between electrons, so that you have here 1/2, because you are repeating the indices of J and K here for as long as they are not equal. You'll be adding the electron interactions. So you have to have 1/2 here because of the repeated occurrence of the pair of electrons. So here you have, in the first term, you have the index J here also, and the index J there. That means that you are considering each electron, each of the Z electrons. So you have to add all the effects of all the electrons. So there are Z terms in this whole thing here. You have 2 Z terms, 2 for the first one and another 2 for the second one, and so on. So it's a long summation. This also, you have for each J and K, you will have here, you have Z times Z minus 1 terms. So depending on the number of electrons, you have a long Hamiltonian, but if you have fewer electrons, you have short Hamiltonians. So in this case, we are assuming that the nucleus, the bunch of protons and neutrons at the center of the atom, is assumed to be stationary. And by the way, if you have just one electron and you have one, and of course you have just the nucleus there, you can use the reduced mass of the system. But unfortunately, um, this will have very small effect to the result, because the nucleus is extremely or much heavier than the electron. So there's a need to solve the Schrodinger equation for the wave function, but in this case you don't have a single electron atom, so you have many electrons, and so you will have to deal with this wave function. But in this case we don't we ignore spin at the moment, because spin can cause much more complications to the problem. So we have to note that the electrons are identical fermions, and that these identical fermions would have a special property such that no two fermions can occupy the same state. So if you include a spin, that would be you have to apply the anti-symmetric combination with respect to the interchange of any two electrons. So again, no two electrons can occupy the same orbital, the same specific orbital at the same time, or the same state at the same time. Here's a note here. Unfortunately, the Schrodinger equation with Hamiltonian equation 5.24 here cannot be solved exactly at any rate, except for the simplest case, Z equals 1 for hydrogen. In this case, you have to do some approximation methods. So let's start looking at the helium atom. We've done hydrogen in chapter 4. Let's do helium atom. So helium atom has Z equals 2. That means you have 2 protons, and then that would also include 2 electrons revolving around it. So the Hamiltonian would have these terms. So this is for the first electron, and this is for the second electron, and this is for the interactions of 2 electrons. So this one is the repulsion of the 2 electrons. This one is the attraction of the first electron with the nucleus, and the attraction of the second electron to the nucleus. The kinetic energy of the first nucleus and the kinetic energy of the second nucleus. So as you have more and more electrons revolving around the atom, then you have more and more complicated Hamiltonian. So if we ignore the last term here, because this if we ignore this one, we would simplify the problem. So the Schrodinger equation can be separated in terms of the particles, in terms of the first and the second electron. So you have here the separation of the wave function with half the Bohr radius, because as you can see, the Bohr radius was A equals 4 pi epsilon sub O h bar square over m e square for the hydrogen atom. But for the helium, you have here a factor of 2, because you are now dealing with 2 protons in the nucleus, and then you have an electron. This is actually the attraction of charges in the hydrogen atom, but in the helium you have 2 protons and then you have an electron. So you have that. That's why you have half of the Bohr radius. So the Bohr radius is now smaller. The energy also, if we recall the energy of the hydrogen atom, you have En equals, the energy of the electron in the hydrogen atom is negative m over 2h bar square. This is E square over 4 pi epsilon sub O, and then you have a square here. So this one here you have divided by this negative 1 over n square. So when you have a helium atom with 2 protons, there is a factor of 2 here. So the energy would be 4 times as great as the energy of the electron in the hydrogen atom. The energy of the electron in the helium atom will be 4 times as great as the energy of the hydrogen atom. By the way, this is the Bohr formula, if you could recall. Bohr formula. So the energy of the 2 electrons now, if you sum up, the energy would be this one here, and En, since they're both in the n equals 1, or say just state n, so you have 13.6 for this one, and also for this one, negative 13.6 n prime square. So in particular, the ground state would be this one here, and the energy would be this. So pi sub O, here you have the factor of 2, because A is reduced by a half, and you have a factor of 8 here because A cube is again reduced by a half, so you have a factor of 8. So if you go back to chapter 4, for hydrogen atom you have phi 100 equals 1 over square root of pi a cube, and you have e to the negative r over a. But this a for the helium atom is now reduced by 1/2, so you will have a factor of 8 and a factor of 2 there. Note here that your phi sub o is phi sub o r1 r2 is equal to phi sub o r2 r1. So in that case, the wave function is symmetric. So why is that? That is compensated by the spin state of the two electrons. So this is a symmetric function. Phi sub is a symmetric function. So the electrons, the two electrons should be anti-symmetric, meaning one electron should be spin up and the other one should be spin down. And that makes the ground state of helium to be a singlet configuration. You know what singlet configuration is in chapter 4. You have 0 0, which is just equal to 1 over square root of 2 you have here minus this spin state. So that's the singlet. One is sorry, this is I made some mistake here. It should be that one. So the helium, if you disregard the third term of the Hamiltonian, will have an energy of negative 109, but experimentally it's only negative 78.97 electron volts. This is not a good agreement. So in that case, the repulsion of the electrons has a large contribution to the energy of the atom. So by the way, the excited states of helium consists of one electron in the hydrogenic ground state and the other is an excited state. So it's not only one is in the ground state and the other one should be in the excited state. If both the two electrons are put in excited state, one immediately drops to the ground state. That's why you have this one. the other one should be in the ground state and the other one should be an excited state. So when it drops to the ground state, when one of the electrons drop to the ground state, it will release enough energy to knock off the other one into the continuum that is energy greater than 0, and that that electron would be ejected from the atom, and so you will only have now one electron left, such that you will now have an helium ion, and then you have a free electron. Both symmetric and anti-symmetric combinations can be constructed from this in the usual way. So you can construct symmetric and anti-symmetric wave functions. The former, with the anti-symmetric spin configuration or the singlet, they are called the parahelium, as I've mentioned you earlier, because the symmetric wave function would have or should have a singlet configuration of the spin, while the latter require a symmetric spin configuration, the triplet, and they are known as the orthohelium. The singlet configuration is called the parahelium, and you have the orthohelium for the triplet state. The parahelium has greater energy compared to the orthohelium counterparts. So you have here that statement. This is the energy level diagram for helium. So if you can see here, if I would magnify this, so you have here, if the two electrons are in the 1s state, with, of course, they have opposite spin, the energy of the helium atom would be 24.46 eV, and if one of the electron is in the 2s, it will increase to -4, and then here you have also for if one electron is in the 3s state, that would mean this energy as well. So you have here this is for the parahelium, and this is for the orthohelium. So this is the energy diagram for the helium. The notation is explained, it will be explained later. The numerical values on the vertical scale are relative to the ground state of ionized helium He+, which is -54.4 eV. To get the total energy of the state, subtract 54.4 eV. Now let's go try explaining the periodic table. So if we ignore the mutual repulsion, the individual electrons occupy one particle hydrogenic states called orbitals in the Coulomb potential of a nucleus with charge Ze. So if the electrons were bosons or distinguishable particles, they would shake all down to the ground state 100, and it would make it would have an impact to the chemistry that we know now. But since electrons are identical fermions, subject to the Pauli exclusion principle, only two can occupy an orbital, and they should be a pair of up and a down, a spin. They should be a pair of spin up and a spin down electron. There are n-square hydrogenic wave function with all the same energy En for a given value of n. So for n equals 1 shell, there are 2 electrons for that shell. For n equals 2, the shells holds 8. For n equals 3, it will have 18. In general, you will have 2 n-square electrons for n shells. Qualitatively, the horizontal rows on the periodic table correspond to filling out each shell. With helium, n equals 1 shell is filled because there are 2 electrons. So the next atom, lithium, which has 3 electrons, has to put 1 electron in the N2 shell. But N2 shell has L equals 0 and also L equals 1. So the third electron would have, wherever it will be put, L equals to 0 or L equals 1, has the same energy, because the energy, the Bohr energies depend on N, not on L. So which L would the electron, the third electron, choose? However, there's an effect of the electron repulsion, and this effect favors the lowest value of L. So it favors L equal to 0 for the third electron of the lithium 3. The reason is the angular momentum tends to throw the electron outward. More formally, the expectation value of R increases with increasing L for a given N, and the farther out an electron gets, the more effectively the inner electron screens the nucleus. So, in other words, the innermost electron sees the full nuclear charge Ze, but the outermost electron sees an effective charge that is hardly greater than E, because of the screening, the charge screening. So the more and more electrons revolve around the atom, the outermost electron sees a net charge that is only around positive E. Within a given shell, therefore, the state with lowest energy is L equal to 0, and the energy increases with increasing L. Thus, the third electron in lithium occupies the orbital 2, 0, 0. The next atom would be beryllium with Z equals 4, which also fits into this state. So you have the fourth electron also in L equal to 0. But if you have a boron which has Z equal to 5, L equal to 0 in the N2 orbital will already be filled up, so that your fifth electron has to fill L equals 1. And continuing in this manner, we reach neon Z equals 10, at which the point at that point N equals 2 shell is already filled, and then the rest of the electrons would have to populate N equals 3 shell. There are 2 atoms, sodium and magnesium, with L equal to 0, and then there are 6 with L equals 1, aluminum and through argon. So they are occupying N equals 3 shell. This is very important bullet here. Following argon, there should be 10 atoms with N equals 3 and L equals 2. However, by this time, you have so many electrons. The screening effect is so strong that it overlaps the next shell. So, potassium with Z equals 19 electrons and calcium with Z equals 20 electrons choose N equals 4, L equals 0 instead of N equals 3, L equals 2. So there's some kind of anomaly here because of the screening. But after that, it goes back, filling up after the 20th electron. So let's consider now the 21st electron. It goes back to N equals 3, L equals 2 from scandium through zinc, and then after that it then now fills up the N4 equals 1 for gallium and krypton. And after that again, at that point, it will jump to the next row, N equals 5, and wait until later until N equals 5, L equal to 0 is filled up. It goes back then to N4 equals N equals 4, L equals 2, and also L equals 3 for that orbital, for the preceding orbital of n equals 5, that's n equals 4. By the way, the L equals 0 orbital is called S, and L equals 1 is called P. S for sharp, P for principal. For L equals 2, that's D. They call it diffuse. L equals 3 equals F for fundamental. And then, yeah, the list goes on. The state of a particular electron is represented by the pair NL, with N the number, giving the shell, and I, or L, I mean, the letter, specifying the orbital angular momentum. The magnetic quantum number M is not listed, but an exponent is used to indicate the number of electrons that occupy the state in question. For carbon 6, you have 6 electrons, and so you have for 1s there's 2 electron, for 2s there's 2 electron, because you have L equals 0 there. And for P, 2p, you have 2 electrons, but it could be in 1, 0, or -1 state, the triplet state, any combinations of the two. So because at 2p you have px, L equals 1, py equals 0, and pz equals -1. So you have that state in at P, or that's just L equals to P, and then you have 3 orbitals, 3 more degenerate orbitals there. So there are 2 electrons in the orbital. There are 2 electrons in the orbital 1, 0, 0, 2 in the orbital 2, 0, 0, and some 2 in some combinations of orbitals 2, 1, 1, 2, 1, 0, and 2, -1. And as I've said, this is the carbon atom, the ground state of a carbon atom. There are 2 electrons with orbital angular momentum quantum number 1, so the total angular momentum quantum number L could be 2, 1, or 0. Meanwhile, the 2 1s electrons are locked together in the singlet state, and also the 2 electrons in the 2s, but the 2p electrons could be in the singlet or triplet configuration. So the total spin quantum number S, or capital S, could be 1 or 0 for carbon. Evidently, the grand total orbital plus spin J could be 3, 2, 1, or 0. There exist Hand's rules for figuring out what these orbitals will be for a particular atom. The result is recorded as this one here, where S and J are the numbers and L the letters. They're capitalized because they are the totals. For carbon, this happens to be 3p0. The total spin is 1. That's why you have a 3, and the total orbital angular momentum is 1. Hence you have the p, and the grand total angular momentum is 0. Hence you have a 0 here. So if we look at the ground state electron configurations of the first 4 rows of the periodic table, we have this one here. For the hydrogen atom, it's just 1s, and you have 2 here for spin 1/2. You have 2 times 1/2 plus 1 is 2, and then you have of course spin 1/2 there, and this is the total spin, and then you have S here for n equals the S is for the total spin would be less than 1, so L would be P would be equal to 1, and S would be less than 1, or that could be 0. So anyway, this is, well, we can use this as physicists, but mostly these are used by chemists, so it's not that important to us, for as long as we know that these are the arrangements of the atom and the physics behind this arrangement. So these notations are not that important. So for the next lecture session, we will be discussing solids. So this is all for now for this lecture. I hope you've absorbed some of the lectures. Maybe not really that 100%, but I hope that at least 50% have you have some understanding. So for any questions, you can write your questions and queries in our Google room. See you in the next lecture.